Welcome back to QubitInk. In this second video, we move from the idea of a qubit to the language of quantum circuits. We will discuss qubits, unitary gates, Bell states, quantum teleportation, and superdense coding. The aim is not only to learn the rules. The aim is to see the beauty of quantum computing. Quantum information behaves differently because the carrier of information is a quantum state. The central question today is simple. What changes when information is carried by a quantum state? A classical bit has a label 0 or 1. A qubit has amplitudes. A closed quantum system evolves by a unitary transformation. Then measurement turns part of that quantum description into classical data. The beauty appears when these ingredients work together. Phase, superposition, and entanglement become resources that can be converted into useful information processing tasks. Here is the route for the video. We start with a single qubit. Then we look at unitary gates. After that, we combine systems using tensor products. That leads naturally to Bell states. Bell states are the first real communication resource in this story. The same shared Bell pair can support two very different tasks. It can help teleport an unknown quantum state. It can also help send two classical bits using only one transmitted qubit. A single qubit is written as alpha ket 0 plus beta ket 1. The amplitudes alpha and beta are complex numbers. Their squared magnitudes add to 1 because total probability must be 1. This is already different from a classical switch. The state is not merely 0 or 1 before measurement. It is a vector. What we store mathematically is the amplitude structure. What we read out from a standard measurement is only 0 or 1. A pure qubit can be any point on the block sphere. That sounds like infinitely much information. But a single measurement does not print out the amplitudes. It gives only one classical result, 0 or 1. The probabilities are alpha squared in magnitude for 0 and beta squared in magnitude for 1. To estimate the amplitudes experimentally, we must prepare many identical copies and measure them in suitable bases. This tension is one of the first beautiful lessons in the subject. A qubit has a continuous state space, but a single observation gives a discrete answer. The block sphere gives a geometric picture of one qubit. The angle theta controls the balance between ket 0 and ket 1. The angle phi is the relative phase. This phase is not a decoration. It affects later interference. One qubit can be visualized nicely this way. But this picture does not scale simply to many qubits. That is already a warning. Single qubit quantum mechanics is geometric and elegant. Many qubit quantum mechanics becomes much larger than ordinary intuition expects. Today we use 4 basic postulates. First, the state of a closed system is a unit vector in a complex Hilbert space. Second, between measurements, the state evolves by a unitary operator. Third, measurement produces classical outcomes with probabilities given by squared amplitudes. Fourth, composite systems are built using tensor products. Teleportation and superdense coding are beautiful because they use all 4 ideas in a compact form. They are not separate tricks. They are clean consequences of the quantum framework. A quantum gate maps ket psi to u ket psi. For a closed quantum system, U dagger U equals the identity. This means the transformation preserves total probability. It also means the operation is reversible. The inverse operation is U dagger. This is why quantum circuits are built from reversible gates until measurement occurs. A classical logic gate may erase information. A closed quantum evolution cannot erase information in the same way. Only measurement changes the story. Only a few gates are needed for today's protocols. The X gate flips ket 0 and ket 1. The Z gate flips the phase of ket 1. The Hadamard gate changes basis and creates interference. The controlled NOT gate flips a target qubit when the controlled qubit is 1. These simple gates are enough to create Bell states, run teleportation, and perform superdense coding. The lesson is important. Quantum protocols are not mysterious because the gates are complicated. They are powerful because simple gates act on quantum states. For n qubits, the state is a sum over all n bit strings. Each string has an amplitude. 1 qubit needs 2 amplitudes. 2 qubits need 4 amplitudes. N qubits need 2 to the n amplitudes. This number grows extremely fast. For 500 qubits, 2 to the 500 is larger than the estimated number of atoms in the observable universe. This does not mean we can read out all those amplitudes directly. It means that quantum evolution can act on a very large state space before measurement. Now we build the Bell state phi+. Start from ket 00. Apply a Hadamard gate to the first qubit. This gives a superposition of ket 00 and ket 10. Then apply a controlled NOT gate. The second qubit flips only in the branch where the first qubit is 1. The result is ket 00 plus ket 11 divided by square root of 2. Each local measurement is random, but the two results are perfectly correlated. A product state separates into Alice's state tensor Bob's state. Each system has its own pure state. A Bell state does not separate this way. It is not saying that Alice secretly has 0 and Bob secretly has 0, or that Alice secretly has 1 and Bob secretly has 1. The quantum state encodes a joint relation. That relation is the resource. Entanglement is useful, but it is not automatically a speedup. It becomes useful when a protocol knows how to spend it. Before teleportation, we must understand why it is not copying. A perfect unknown state copier would take ket psi ket 0 to ket psi for every possible ket psi. But quantum evolution is linear. If ket psi is a ket 0 plus b ket 1, the controlled NOT style copying attempt produces a ket 00 plus b ket 11. A true copy would contain extra cross terms, a b ket 01 and a b ket 10. They are not the same state. This is the no cloning lesson. Teleportation transfers an unknown state, but measurement destroys the original. Alice has an unknown qubit. Its state is alpha ket 0 plus beta ket 1. She does not know alpha and beta. Alice and Bob already share one Bell pair, prepared before the protocol begins. The task is to recreate the unknown state on Bob's qubit. Alice may use local quantum gates and measurement. She may also send 2 classical bits to Bob. The resource identity is this. 1 shared E-bit plus 2 classical bits can transfer 1 unknown qubit state. Look at the circuit from left to right. The lower 2 qubits first prepare the shared Bell pair. Alice holds the unknown qubit and her half of the Bell pair. Bob holds the third qubit. Alice applies a controlled NOT gate and a Hadamard gate. Then she measures her 2 qubits. Those 2 measurement outcomes are classical bits. Bob receives those 2 bits and uses them to choose the correction. The correction is one of the Pauli operations, identity, x, z or zax. The algebra shows where the magic sits. The initial state is ket psi times phi plus. After Alice's gates, the full state can be regrouped into 4 branches. If Alice measures 00, Bob already has alpha ket 0 plus beta ket 1. If Alice measures 01, Bob has the x-flipped version. If Alice measures 10, Bob has the z-flipped version. If Alice measures 11, Bob has the x and z modified version. Alice's qubit result does not reveal alpha or beta. It only tells Bob which Pauli frame his qubit is in. The correction table summarizes the whole protocol. For outcome 00, Bob applies identity. For 01, Bob applies x. For 10, Bob applies z. For 11, Bob applies zx. In every branch, the unknown amplitudes alpha and beta remain present in Bob's conditional state. That is the central point. The branch label is classical. The quantum information has moved to Bob's side, without Alice ever learning the state. Teleportation teaches resource conversion. A shared Bell pair is not a message by itself. Alice's measurement alone is not enough. The 2 classical bits alone are not enough. But together, shared entanglement and classical communication can replace a direct quantum channel for one unknown state. There is no faster-than-light signal here. Bob needs Alice's classical message before he knows which correction to apply. The protocol respects relativity and the no-cloning theorem. Superdense coding is the reverse lesson. Now Alice wants to send 2 classical bits. The possible messages are 0001, 10, and 11. Alice and Bob again start with one shared bell pair. Alice acts only on her half of the pair. Then she sends that 1 qubit to Bob. With his own half of the bell pair, Bob can recover the 2 classical bits. The resource identity is this. 1 shared E-bit plus 1 sent qubit gives 2 classical bits. In the superdense coding circuit, the first part prepares the bell pair. Alice then applies an encoding operation to her qubit. That operation is chosen from identity, C, X, and XZ. After Alice sends her qubit to Bob, Bob holds both qubits. He applies the inverse of the bell state preparation circuit. That means a controlled NOT gate followed by a hammered gate. Then a computational basis measurement reveals the 2-bit message. The single transmitted qubit gets its meaning only together with Bob's half of the bell pair. The 4 messages become 4 orthogonal bell states. Message 00 leaves phi plus unchanged. Message 01 applies Z and gives phi minus. Message 10 applies X and gives psi plus. Message 11 applies XZ and gives psi minus. Because these 4 bell states are orthogonal, Bob can distinguish them perfectly after the decoding circuit. The 2 classical bits are not encoded in Alice's qubit alone. They are encoded in the joint 2-qubit state. The algebra is compact. Start from phi plus. Apply Z on Alice's half, and the state becomes phi minus. Apply X on Alice's half, and the state becomes psi plus. Apply XZ on Alice's half, and the state becomes psi minus. So Alice's local Pauli operation selects 1 bell state out of 4. Bob's decoder maps the bell basis back to the computational basis. Then a final measurement gives the 2-bit classical message. Now compare the 2 protocols. Teleportation sends an unknown quantum state without a direct quantum channel. Superdense coding sends 2 classical bits using 1 transmitted qubit. Both consume shared entanglement. They are not just clever circuit identities. They teach that communication resources can be traded, counted, and transformed. This is one of the most beautiful ideas in quantum information. Information is physical, and the physical form of the resource changes what communication can do. Let us summarize. A qubit is not powerful because 1 measurement reveals infinitely much. It does not. A qubit is powerful because amplitudes can evolve, interfere, and become correlated before measurement. Unitary gates preserve the quantum state structure. Measurement converts part of that structure into classical data. Entanglement creates joint states that cannot be reduced to separate local pure states. Teleportation and superdense coding are our first clear examples of entanglement as a working communication resource. In the next video, we move from circuits to algorithms. We will study Deutsch's algorithm, the Deutsch-DAS algorithm, quantum parallelism, and oracle circuits. We will also be careful about what quantum speedup really means. Not every quantum-looking circuit is faster than a classical method. The question is sharper. Which problems allow amplitudes and interference to reduce the number of steps needed? That is where quantum circuits become quantum algorithms. The main source for this video is Quantum Computation and Quantum Information by Michael Nielsen and Isaac Chuang. The implementation examples use Qiskit circuits for bell state preparation, teleportation, and superdense coding. The purpose of QubitInk is to build these ideas slowly and correctly. The mathematics matters, but the story also matters. Quantum computing becomes easier to understand when we see the physical resources behind the equations. Thank you for watching QubitInk. Quantum computing, one idea at a time. In this video, we saw how qubits, unitaries, measurement, and entanglement combine into real protocols. In the next video, we will use the same circuit language to build our first quantum algorithms. See you in the next episode.